What we did last time was the indefinite integral, where we saw that this operation here, this symbol here is called an integral. And then what it means is, or not what it means, but what you do is, whatever is here in between the operation and the quantity here, dx, you find the antiderivative. That's all. As far as you're concerned last time, that's what I told you to do. Whenever you see this, it just means find the antiderivative of the function here, and then you write a capital or uppercase here. It's just a style, if you like. You don't have to write like that, but that's the style that most people use. And this thing here inside the integral has a name. So it's called an integrand. So the quantity that's inside the integral there is called an integrand. And so I'm talking about this thing here. So just about communicating it. I don't think I explicitly told you what it was called last time. Many of you asked during class, not just your section, but the other section as well, what the heck does this dx mean? So over here, there's a dx here, and many of you are wondering, what does that mean? So by the end of today's lesson, I'll give you a better understanding of what the dx means. And then next week, we're going to tie it all together, put a big bow around it, and that represents the unit for antiderivatives and some introduction to integral calculus. Of course, after that, you have a test, and that will be your first test, which is in week 5. And it's like last semester, it'll be on the MyLab platform. And of course, I'll give you a set of hints as well, as I have done in past tests. So, moving on. We're moving on to a new topic today, and this all ties together. Remember, it's one big story that is going to come to a climax next week. So now we're talking about this, the area under a curve. And when you look at this, you might be like, oh goodness, what the heck is going on here? You got this, look at this algorithm. It kind of reminds me of the optimization stuff at the end of last semester. So what we're trying to do here, and I just want to emphasize it, today we're trying to find the area under a curve approximately. So focus on that word there, approximately, okay? I don't know if I should underline it or highlight it. Now, if you're wondering, how do you find the area exactly? I'll just say that down here, the area, if you want to find it exactly, is actually this formula here, which I'm going to reveal to you next week. So, I'm going to discuss it further. So, the area, if you want it exactly, is the antiderivative or is related to the antiderivative. So that's kind of how everything ties together. But as far as you're concerned today, we're looking to find the area under a curve approximately. And the way that we're going to do that is by using rectangles. So if you go to your notes, or you can follow me on the screen here, we're going to go to example 58. Example 58 is not an example with calculations. It's just describing the process that I have here, but a little bit more visual, because I think that you'll appreciate the visual process more than a bunch of formulas. So this is something that perhaps some of you have read before class. If you've read this already, that's very good, but you were not asked to read it before class, so don't worry about that. I'll walk you through it. So I'll use my stylus here and kind of draw stuff as we're going. So here's a function f of x. You see the purple curve here is f of x. Your goal, or our goal I should say, is to find the area from here to here, okay? So we're trying to find this purple area. That purple area, if I gave that to a kid, let's say I give that to a kid in grade 5, they're going to be like, I can't find that area. Look, it's all curved. Like, what the heck is it, right? Like, if that was a straight line, anybody up into a certain age for sure could figure that area out. Like, if this is a trapezoid, like, see that shape? There's a trapezoid. If you had a trapezoid, that area is a joke. It's just the formula for a trapezoid. But this is definitely not a trapezoid. This is a shape that has, it's not a polygon. So how the heck do we find this area? So our focus today will be to find the area by approximating it with rectangles. See all these rectangles here? There's 5 rectangles. So that's the first quantity. That's the first quantity that is described in the algorithm. So how many rectangles are we using? We're using 5 rectangles. So we say that n equals 5. So that's the first symbol in the process, or the first parameter that you have, is the number of rectangles. You can also refer to this as the number of intervals, because each rectangle, as you see at the bottom on the number line here, each rectangle has an interval. And that interval depends on, well, it depends on the width of the interval, depends on where you start and where you finish. So we're trying to find the area from A to B. So that's what you have here. See, we're trying to find the area under the function from A to B. Now, each interval is a certain width. So you see here, delta x here is the width of the interval. So I'll just take this interval right here. This thing here, from here to here, that width there, we call it delta x, okay? So delta x, we're going to assume that all the rectangles are the same width. You can do things with computer programming, and if in some of my stuff that I've done in grad school and in undergrad, as it was more like applied mathematics courses, like the real hardcore kind of programming courses, you could actually have intervals that are different widths. But for the purpose of the fundamental theory that I'm trying to show you here, when it was first developed, the rectangles were all the same width. And for anything I ever ask you to do, the rectangles, at least in the examples I have here, will be of the same width. So let's take a look at these rectangles in a more close fashion. So I'm not really asking you too many prompt questions here, but maybe offer me some insight into the rectangles. So we have 2 diagrams here. We have the diagram on the left and we have the diagram on the right. Can someone comment in the chat? What's the difference between the 2 diagrams? Just tell me in your own words. What's the difference between the 2 diagrams? Just comment in that chat. It's the same function, and we're still going from here to here. So let me know in that chat what you think the difference is between the 2 diagrams. Yeah, I like what you said. So I want to mention that f of x here is the same for both. So f of x is not changing. Okay, it's the same graph. But yes, I like the idea of below and on top. Can you expand on that, Asim? What are you trying to say there, below and on top? Tell me a little bit more. I like what you're saying there, but yeah, the way it's measuring it, yes. The way that it's measuring it is weird. Like here, which graph, let me say it like this, which graph is going to underestimate the area? Which graph underestimates the area? The first one, yeah, the left one. You see here, these rectangles, look at the staircase they make. That's under, whereas this one's over. So I'm not saying that this one here will always be under and this one will always be over. If this graph was decaying, if f of x is going this way, then you would have the opposite effect. So how are we actually getting the heights of the rectangle? And that's discussed right here. And it's probably the most crucial thing to the process here. On the left figure, the height of the rectangle is the y value at the left endpoint of the interval. I know that looks scary to people because it's a pretty long sentence, but let me break it down for you. Let me break it down for you. See this? See the first rectangle here? Take a look at the first rectangle. This one, we'll call number 1. This rectangle occurs on this interval. We determine the height of the rectangle by using not this point on the, not using the x value here, but we're using the left x value. If you go to this rectangle, same rectangle, same interval. We have our interval here, but we're not going to use this one. We're going to use this point right here. So that's how we get the height. See, we use the y value on the graph over here, or we use the y value on the graph over here. And depending on whether you use the left endpoint, whether you use the left endpoint over here or the right endpoint, you're going to get a different rectangle height. And which one's better? Well, they're both okay. It doesn't matter which one you do because it's an approximation. Estimates are approximate, and the purpose of them is to give you an idea of what the answer is, but not to be perfect. However, we do know that somewhere in between the left and somewhere in between the right, in this case at least, there is a likelihood that the true area is there. That's not always the case, but the idea is that if the rectangles are thin enough, or there's enough rectangles, that you can say that there's always kind of like a sandwich effect. So we're starting to get an idea of what's happening here. So let's write that down in our own words. Let's write that down in our own words at the bottom of the page. I'm just going to make comments here, and then I'll show you how this connects to the algorithm, okay? So this is the process that we're talking about here. It has comments at the bottom of the page, but I'm just trying to tighten up my notation here. Step one, is, okay, so first of all, you choose n. Or if you don't choose n, I just tell you what n is. And then step one is you find the width. And once you have the width, step two is you divide the interval into points. Step three, you find the height of each rectangle. And then step four, you add up all the rectangles. I'll just say here, find the sum of the areas of all the rectangles. Let me know in the chat. Just let me know in the chat, everybody. I want you to really give me, hold me to the fire on this one. Does that make sense? Do those 4 points make sense to you? Please let me know if there's any clarification that you need. Let me know in that chat if you need any clarification. I didn't do any calculations yet. I'm just trying to show you the idea. That's all. Yeah, it's from 10 to 11. That's right. Quiz is from 10 to 11. You're welcome. Any questions about this? Any comments? Like, does that make sense? How do you get in? Good question, Anthony. And choose. Maybe choose n is not your choice. You are either choose or you're told. Okay? So at least in this course, I will just tell you, Anthony, I want you to use 10 rectangles or use 5 rectangles. And in any question that you get on an evaluation, it'll tell you explicitly how many rectangles to use. Any other questions? So I haven't dropped the formula on you yet, but I want to take this little summary here, and I want you to compare it to the algorithm that I presented here that might have taken you aback earlier. I have to shrink the font here, though. No, the ID is just your student number. On MyLab, it's going to ask, when you log into MyLab today, it's going to ask you for your student number. It's just because it's the new semester, and I just put a little ask for you to put your student number because it helps me upload and download grades easier. Instead of uploading and downloading your grades by your name, I upload and download your grades by a student number, which you can't screw up. If I misspell someone's name by accident, It's a little bit complicated, and plus people like to be referred to by different names than what they're presenting on the screen. Like if someone's name is Michelle, but they want to be called Michael because that's in my other section. Like I want it to be correct, okay? Anyway, over here, those 4 points represent the 4 steps. You see those 4 steps here? So those steps that I was talking about are right here. Step 1 is find the width. Step 2 is break down the interval into points. Step 3 is find the height using either the left or the right. And step 4 is to add them all up. See, total the area. So we have a procedure that is exactly what we're going to be practicing for today. And we're going to do this about I think it's 4 times. We're going to do 4 questions. They're going to be a little slow. And then after we're done that, we're going to go and do, we're going to tie it together to how it relates to the antiderivative. So please turn to example 59. And in 59, I actually have a breakdown of how you do it for a line. So this one here, I'm going to actually go through it on the next example and take you through it really slow so that you understand the entire process. And I've done it in a way that's really easy to do. So, and you'll see what I mean. I'm going to be using tables. If you look here, though, this is the kind of the formal way of doing it. And it looks a little scary. I realize it looks a little scary. But I'll show you how you don't have to write it this way at the beginning. You can just use a table or some sort to organize the numbers. No. The test is the quiz. The quiz is always based on the previous week's lecture. So it's based on last week. I'll never test you on something the same day you learn it. That's absurd. I won't do that to you. Okay? You're welcome. So here's our first question, everybody. And it's the same calculations as the previous page, but that previous example 59, I'm asking you to look over that example. I'm going to give you some time at the end of class today. So our quiz is at 10 o'clock, but let's say 10 to 10 or 20 minutes to 10. I want to give you 5 or 10 minutes on your own to reflect on example 59, to go over back on that and to look at it and make sense of the notation. But what you see in example 60 is really a nice template to do things. This template here is mine. What I mean is that you're not going to see it like this in most textbooks. So if you want to do this strategy that I'm showing you, I would really, really pay attention to how I set this table up, and I would be prepared to construct a table like this to help you do test questions, because it's important that you really have a good grasp of how to do this process. Obviously, this is going to be on your test, your first big test, which is 2 weeks from now. I haven't set up your test yet, so please don't ask me about the test right now. I'll give you information about the test next week. Anyway, let's go through this process. Find the approximate area. So the key word is approximate area. And it says here to use a right endpoint. And I'll just tell you flat out, every example that I have here is a right endpoint approximation, meaning that in the original page that I showed you, I'm always going to do it this way. I'll put a happy face here, not because this is better. That's just the way I'm going to do it every time. And when I give you your evaluations, I'll try to choose ones that have right. Although it might have left or right, it doesn't really matter anyway. Honestly, it's the same amount of work, and this table that I'm using can cover both options. So here's the process. We want to find the area approximately from x equals 0 to x equals 2 using 4 intervals. So the first step is to figure out how wide each interval is. I don't think you need formulas for this, people. I don't think you need formulas for this. Can someone let me know in the chat, how wide is each interval? Remember, it starts at 0 and you finish at 2. Anthony, was that the hardest calculation to do? Was that a hard calculation to do, bud? Absolutely not, right? That was easy? Easy peasy, right? So we already know the answer is 0.5. So most of these calculations, you'll find that you do not need a formula for. You can just plug in numbers. But I'll come back here. This is 0.5. I just want to emphasize now that the next part of the process is to figure out what A and B are. So let's talk about that in the question. Our interval starts at 0 and it finishes at 2. So that's what A and B are. A and B are where you start and where you finish. See, that's A. And this guy over here, oops, this guy over here is B. I'm going to turn my camera off. I think it's starting to lag a little bit. Okay. So we have here 2 minus 0 over 4. So that's how I got 0.5. Are there any questions about that calculation? Well, anyway, that's step 1. This is step 2. And this is step 3. And this is step 4. So that's the algorithm. Those are the 4 steps. So now we want to find the locations. So this stuff here where I say x0, x1, x2, x3, these represent the x values. So if I go on the grid here, x0, x1, x2, x3, x4. x0, x1, x2, x3, x4. Okay? Notice that we start at 0. Why would we want to start at 0? Because if you have 4 rectangles, that means you need 5 values of x to enclose them, because it's always 1 extra. So it would make sense to start your count at 0. That way, by the time you get to the end over here, you are at number 4, and this number 4 is what n is. See, n is 4. So it's all nice and consistent. So by having that consistency, it's easier to document and to label things here. So our values for x are going to be, you're starting at 0 and you're finishing at 2. Someone type in the chat what these three numbers are. Use commas. Tell me what these numbers are. What's x1, x2, x3? Let me know in the chat. Thank you, Gianluca. So I'm going to copy down your answer. Thank you, Amir. So we have 0.5, 1, and then 1.5. You didn't need a formula for this, but you might be wondering, how do I fill this in fast? Well, what you do is you started this. This is A. Let me put A here. That's A, and this is B. So x0 here is also A, and the final one is also B, because that's the interval endpoints. And then to go from here to here, as you hop along here, whatever, all you're doing is adding delta x. You're just taking this number, so 0 plus this is this, plus this is this, plus this is this, plus this is this. So you can kind of keep on adding the delta x to move along. Okay, well that's good news. The next part of the process is to find the heights. So let's get a different color here. So the height of each rectangle, it's directly related to this. See, there's x and there's y. There's x and there's y. So I'll just talk about one of them for a second. I wish we had an equation. Obviously, I'm being facetious. I wish I had an equation that relates y to x. In other words, if I have x, it gives me y. What's the equation that relates x and y? Where is that? Is that anywhere in the question? Thank you, Jai. It's right here. So if you want to find the height, it's just the formula in the question. It's y equals 2x plus 1. So what you're going to do is you're going to take 0 and plug it in here. If you plug in 0 here, what's the y value? Thank you. If you look on the graph, that's this point right here. That's this point right here. And then you can get the next one by plugging it in, and you're going to get this point, and so on. It turns out that this one's pretty boring because it's just 1, 2, 3, 4, 5. So you could get these numbers from reading them off the graph. There they are, 1, 2, see the heights, see the y values, 1, 2, 3, 4, 5. And this part here is the easiest part because you just take the y value. I'll put a subscript here for these, so it looks like the algorithm I showed you. If you want to get the area I is equal to, I'll just say area I is equal to the y value times delta x. In other words, if you want to find the height of a rectangle, you'll take the y value here and you'll multiply by delta x. So that's 0.5, and that's 1, and then 1.5, and then 2, and then 2.5. Hopefully I've gone very slow and you can understand the process that I've showed you. Can you guys let me know in the chat? Do you understand the process that I've been presenting here? How do you feel about this process? Let me know in the chat, please. I want to see at least 10 people. That's 3, 4. I'm going to count it out. It takes us all day. That's 5. Thank you, Joshua and Khalid and again. Anybody else? Any feedback? 4 people. I'm going to count to 10. Okay, that's 8. No, 7. I didn't know how to count today. There you go. 3 more. 8. There should be like a timer with like a checkbox that, and it won't proceed until like everybody kind of scans their card or something. 2 more people. Let me know that it's good. Thank you, Christopher and Mateo and Giorgio. Okay, Ethan. Thank you, Ethan. Clutch performance at the end there. I'm gonna give the goal to Ethan with an assist from Khalid and Mateo. So those are the NHL 3 stars last night. Anyway, let's go back here and find the total area. So remember we talked about area and we talked about how the rectangle could have different heights. So in this case, I'm asking you for the area determined by using the right endpoint of the interval. So if I look back at this diagram, see these 5 red dots? Which one of these 5 red points did we not use? Was it the first one, the second one, or better yet, which value of x at the bottom do we not care about? That's right, Jai. It's the first one. We don't care about the first one because we're using the right endpoint. Trying to find a color here. Let's use a green. Let's use a little bit of a green here. So when you use the right endpoint approximation, we actually don't care about this number here. I don't want to completely obliterate it, but I do want to like really just knock it out like that, because this point here is not for the right. These are the right endpoints. See, this rectangle, the first rectangle is this tall, and it was determined by this point over here. And then the second rectangle was this tall, but it was determined by this point over here, and so on. So for that reason, we reject the first one. Okay, hypothetically, if the question was to use the left endpoints, then you would throw these ones away. You would throw these ones. You don't keep those ones if you're going to use the left endpoints. But in any case, it doesn't matter. It doesn't matter if you fill this table in with all of them. So if you want to use the right endpoint, the answer is just add up these guys. Add up those numbers, please, someone. Well, that's pretty easy. I should do it myself, I guess. Is that 7? Thank you. That's 7. Awesome work, people. So you might be wondering, okay, that's all great, but is that answer the correct answer? Is that the true area? Do you think that's the true area, like the exact area? No. Do you think it's too small or too big? Tell me about that. Do you think it overestimates or underestimates? Yeah, it's too big. It's over, right? That's good work. I'm just locating something on my hard drive, so that's why I'm paused. Okay. So, how the heck do we improve on that? How can we improve on this? Well, what you can do is you can add more rectangles. How about that, eh? You could just add more rectangles. Now, before I do more rectangles, the next example, by the way, the next example is the same thing, except here. We're going to use 10 rectangles instead. Before I go there, if anybody's like, why the heck are you doing this, guy? John, why are you doing this? This is the easiest area to find. Because that's a trapezoid. That's a trapezoid. Like, why even bother doing all this stuff when it's a trapezoid? The reason I'm doing it is because it's your first time seeing this, so we should use something really easy to work with before we do something more difficult later. So anyway, we did the process here for 4 intervals. So let me just put a box on that. Now we're going to do the exact same process, but with 10 intervals. So let's do this. Let's try to get this one. Let's bang this one out here. Get it done. Get her done. And then we'll see how that goes. So I'm going to scroll down a little bit, maybe up to there. I think that's good. And I'll slowly build up the answer again. So in this case, no picture though, people, because the picture probably, when I was drawing these, I gave up and I said, look, okay, I drew one here. That's enough. I'm just kidding. I think I have a picture of it over here somewhere. No. I actually had a picture of it on an older version and I got rid of it because I couldn't annotate the figure very well. So I didn't bother including it. Anyway, what's delta x? Can someone tell me delta x for 61? Let me know in the chat. I want to see a bunch of people saying it. 0.2? Anybody else? Okay. Nice save, Anthony. Yeah, it's 0.2. Thank you. It is 0.2. That's correct. So how do we get that? I'll remind everybody there's a and b. So it's b minus a divided by n. So it's 2 minus 0 divided by 10. It's 2/10. I'm trying to, my stylus is glitchy sometimes, as you know. So that's 0.2. Now we're going to find the locations. So the locations start at 0 and they end at 2. And why is that? Because this is A and this is B. And then how do you fill these in? Can someone tell me what x5 is? Anybody have x5 already? 1. I had to count it out like a baby, sorry. There you go, that's a 1, that's good. So if you want to fill this in, you're going to go here and you're just going to keep on adding 0.2s. So it'll take me longer to write it here than it will probably for you to actually do it yourself. So bear with me as I struggle to write these down. As we get to more complex examples later on in this hour and after the break, I'm probably just going to copy and paste the table from my personal notes. And yeah, I'll share these notes at the end of the class as well, as per usual. So now that we have those x values, we can find the y values. So the y values, well, there's the function. Here's the function, y equals 2x plus 1. So that's how you find the heights. So if we do that here, I'm trying to pick a color. So we would write here y equals 2x plus 1. I'm not putting subscripts, but you can appreciate that's the formula that I'm using. So that'll be 1, and this will be 5. And all the in-betweens, I'll do a couple of them here. So if you do 0.2, 2 times 0.2 is 0.4, so that's 1.4. And because this function's linear, I'm going to cheat here. It's going up by 0.2 every time. Now, this is where I'm saying, rather than me scribble these on paper and embarrass myself, I'm just going to drag the my table entry. This is from the solution manual, my solution manual. I'm plagiarizing myself. Good enough? That's fine. That's fine. Look at that. Like it never happened. Okay, anyway. Now that you have the height of each rectangle, I'll scroll down here, and we're going to find the area. We're going to find the area by taking the y values and multiplying by delta x. So 1, I'll do the first one in green and annotate it. So 1 times 0.2 is 0.2. I'll do another one here. 1.4 times 0.2 is 0.28. And unfortunately, my friends, this is really annoying because you're going to have like decimals all over here. And rather than clutter it with my decimals, I'm going to just copy and paste the rest of the table. Obviously, if this was like an evaluation setting, I would give you ample time in the question. It would be a much more comfortable discussion here. I'm not going to ask you to be able to do, I don't expect you to do this in like 10 seconds like I just did. I expect you to be able to do, I expect you to fill this table in 5 minutes. I think 5 minutes is a fair number. I don't think 5 minutes is too long for this because this is counting, this is plugging in, and this is multiplying. So there's a lot of procedural stuff. And I'm not really a fan of using too many rectangles. So I'll say that 10 is probably the most I'd ever ask you. In reality, I probably want to use a lot less than 10. So when I'm creating or searching for test questions, I'll try to find ones that don't have a very high value for n. Like less than or equal to 5 is my goal, but I'm not going to promise you that. But I'll try to pick a low number. Anyway, in this question, I'm asking you, and most likely is what you'll see is the right endpoint approximation. So because we're using the right endpoint, not the left endpoint, to construct the height, can you tell me which number in this list here, which number in this list do we throw away? Do we discard? Which number do we discard or get rid of? Thank you, Amir. Yeah, this one here. So what you want to do now is right here. And okay, maybe it's right here because you can see that it's 1 to 10. But yeah, you add those up. So I'm going to put that answer here, and the answer is 6.40. The answer is 6.40. So now we have an interesting scenario. I'm going to write this on the next page. If you don't mind, I'm just going to continue here with the page. If you were copying the table, my apologies. It's not really too big of a deal to copy that table down. But anyway, when we used, what was the answer when you used 4 rectangles? Can someone remind the class? Thank you, Sean. Okay. So if you were to use an infinite number of rectangles, then you get to the exact answer. And I'll just mention here, we're not proving this in this course. But the exact answer, So what is the exact answer for the area? Anybody want to guess what the exact answer is? That's right, Sean. The exact answer is 6. I don't care if you write down units squared. And I'm not testing you on that right now. Okay, this is just extra. This is what I'm talking about today. What we just did together is the blue stuff. The red stuff is just a little bit for later. If you were to use an infinite number of rectangles, you get closer and closer to a value of 6. And that is the true area. So what I want to do now is start off the next example. So we're going to go to example 62. And we're going to do the process for a parabola. This is a parabola this time. And notice that there's 5 and then there's 10. So there's a 5 and there's a 10. And then after that, I'm going to talk to you about how this relates to the antiderivative. And that'll be the end of our lesson. Now, it seems like a very slow lesson today, but I got to tell you, I'm just going to put that camera on and tell you guys for a couple minutes. It's really important to me. Over the years, I've helped a lot of people learn antiderivatives, and like whether it was like just instructing or as a TA or whatever. And the one thing that I always got bothered by is that when this is instructed, people just gloss over it, and they just and usually what you'll get is like the hardcore formulas and just do it. And then the students are like, struggling to get a foundation. I'm the opposite. I don't want to hammer you with the most extreme part of the theory today. And I'm not doing that in this course because we have a very limited number of hours to talk about this stuff. So I'd rather talk to you about how you construct the rectangles, how you get the values, and for those that want a more robust or maybe a more rigorous, I should say, connection to the theory, I can definitely point you in the direction for that stuff. But yeah, that's not my exercise here. Your ultimate goal is coming out of this course that you understand a little bit about antiderivatives and you understand how it relates to areas. So let's go to this question and let's hammer out question 62 together. And then after that, I'll talk to you about next steps. So anyway, let's find the approximate area under this parabola. There's your parabola. See, there's the parabola. Whoops. So it's not a straight line anymore, so it's not going to be easy numbers anymore. You actually have to get your calculator out and kind of punch stuff in there. And we want to go from x equals 2 to x equals 3. So that's A and B. And we want to use 5 intervals. There's 5 intervals, okay? So what's delta x? Anybody in the chat? Let me know what delta x is. That's correct. 0.2 is correct. 0.2 is correct. Sorry, just fixing something here. So let's do that calculation. So we have 3 minus 2 divided by 5 is equal to 0.2. Now, whoops, drawing that equal sign funny. Now we're going to actually chop up or divide up the domain into those points. So if there's 5 intervals or 5 rectangles, then you know that there are 6 points in the interval. There's always that extra point because you have to start somewhere and finish somewhere. So we're starting at x equals 2, and we're finishing at x equals 3, and we're going to keep on adding 0.2 to fill up that table. So 2.2, you can just count it out. You don't need fancy formula for this. You do need the fancy formula if you ever want to do the actual proof, which is beyond the scope of this course, but there you go for that. Now that you have the x values, you can go and get the y values using the equation, the parabola in this case. So even if, I just want to tell you guys, even if the formula was absolutely like nasty right here, even if that was the nastiest formula of all time, let's say this formula had log in it or sine or it had an exponential, or it just had a combination of a bunch of stuff that scares you. Who cares what it is? You just plug in x to get y because you're just finding a y value, and this is basically a table of values. This here is a table of values. Just like you did a table of values in grade 8 or grade 9 or whatever, that's all you're doing here is table of values. So we're going to do 2, and you're going to put it in here. 9 minus 2 squared is 5. Oops. There's 5. I'll do the last one over here. 9 minus 3 squared is 0. And then I'll do one more in red, and then I'll copy and paste the numbers from my solution manual. So that's 4.160 Heck, I'll just write it in. 3.240, 2.240, and finally 1.160. How are you doing there? Let me know in the chat. How's everybody doing with this? You feeling all right with it? Thank you. Unfortunately, I don't have you beside each other. It would be really nice. Usually in class, what I'll do is I'll pair people up or put them in threes as they're sitting at their desks anyway, and I'll get them to work together and fill the tables in. So I apologize that I'm not really doing that with you here, but what I'll do in compensation for that is give you a little bit extra time during the break to work out one of these questions on your own. So anyway, to get the area, you're going to take the y value and you're going to multiply it by delta x. So the area is going to be y times delta x. And so if you do that here, let's take 5. What's 5 times 0.2? Well, that's just 1. I'll put a box. Whoops. I'll put a box there. So that's 1. I'll do this one as well because this one's pretty easy. It's 0. And then we can put some values for a in between here. So we're going to take all these numbers here and we're going to multiply them by 0.2. So that's what I'm saying. So if you take this one times 0.2, you get 0.832. Now some of you might be wondering, how many decimal places should I use? Honestly, the more the better. Use the more the better, okay? Because I'm the person actually looking over your evaluations, if your answer's off by a little bit, I'm not saying you're being lazy with your rounding, but if you don't round enough, I can tell that your answer's off by a bit. And I'm not going to ruin anybody, but if you're off by whatever the question's asking, by more than that, like if the question says to the nearest tenth, but you're off by like a value of 2 on that significant digit, I might deduct a little bit, not because I hate you or anything, but because I want to reward the people that take the care to do the extra precision or accuracy and really respect that. Anyway, it's not a big deal, and it's a very minor deduction, but I want to reward the people that do that, go for that extra level of detail. We're going to use 4 rectangles here, and we're using the right endpoint approximation. Which of these numbers do I throw away? Which of these numbers do I throw away? Thank you. You throw away a naught. So if you add these up here, if you add up these numbers here, what do you get? Let me know down here. What do you get? Beautiful. 2.160. Thank you for writing down units squared, Jai. By the way, on the test, you don't have to write units squared. That's just me talking to you to give you that level of detail. But I won't write it here, and just on an evaluation, I won't write it either. But very, very nice that you put that, Jai, that you remembered that I did that on the previous page. That's good work. So we're going to take a break very shortly, I promise you. But I want to draw a picture. I'm going to draw you a picture before we go to that break, because I want you to understand about these numbers, what's going on. So if you were to graph this, if I take this parabola and I graph it, and people, don't worry too much about how pretty my picture is. I just want you to get an idea. I want you to get an idea of what's going on here, okay? So that's the actual graph. That's x equals 3, and that's x equals 0. And we're trying to find this using rectangles. So 5 rectangles. So I'm going to try to draw 5 rectangles, and just cross your fingers that I can do this well, because my computer is very glitchy when it comes to this stuff. And now let's find out the heights of those rectangles. So see these numbers right here? These numbers right here, are as follows. So there's 5 of them. Ready? So 4.160 is right there. And then this height here is 3.240. Obviously, everybody, it's not to scale. That's why I said to you, please don't take me to scale here on this one. 2.240. This one here is 1.160. You see those heights? And what was the height of the last rectangle? Look at that. What's the height here? It's 0. That's this height. So that's actually 0, but I'm giving it a little bit of a gap there so you can actually see it on the screen, but it's 0. The point here is what I'm trying to say is that in this case, we are underestimating. Let me say that again. We are underestimating the area. And that's okay. This obviously, everybody in this group here knows that this area that I'm shading is non-zero. There is a number there. It's not 0, it's more than 0. But by putting a 0 here, it's not a disaster. Because if you go with more and more rectangles, then this error here, it'll get skinnier and skinnier and skinnier, and it won't matter. It'll diminish. And with an infinite number of rectangles, it'll be gone. So anyway, right now it's 8:56. I'm going to give you guys 15 minutes, 1-5. So actually, I'll give you 20 minutes, okay? Is it 8:56, 9:50? I'm just trying to think. I'll give you till you have a break until 9:15, okay? But it's not just a break, it's a working break. I want you, like, if you want to do this or not, do 63. So let's just talk about the answer to 63 here. So hopefully you had a solid break to practice this. I'll just kind of give you the highlights here. So in this case, it's b minus a is 3 minus 2 divided by 10, because that's a and that's b, and n is already there. So that's 0.1, and that's a here, and that's b here. And then as you hop along from box to box, you're just adding 0.1. To get the y values, you remember you use this formula to get the heights. So you're just plugging in x to get y, and then to get the area, you're taking the y value and you're multiplying by delta x. Since we're using a right endpoint approximation, we don't care about a0 or a0 here. So I'll just kind of, I'm trying to keep the 5 visible so you know it's still there, but you're going to reject that value. So with that in mind, my friends, we are looking pretty good. But now I'm going to dip back here. And I'm going to go back to that question. Remember the one we did at the beginning today? We spent a good 40 minutes on this. And I said to you that the area, we got an answer of 7 for this equation here, y equals 2x plus 1, from x equals 0 to x equals 2. We got an answer of 7. It's pretty good. Too much, though, was overestimating. So we went with more rectangles. We went with 10 rectangles. And you got an answer of 6.4. And then I mentioned to you on the next here, in as a little footnote, I guess, and I said to you the exact area is 6. And some of you probably are wondering, how the heck did I get that number? Well, for this question, it was okay because the shape, the exact area, is a trapezoid. And that's not an issue. That's easy to do. But over here, in this question, the shape is, again, not a polygon. That is not a polygon. So I can't just tell you, hey guys, what's the area of that? Well, if you said, oh, it's like a circle or something. No, it's not a circle. It's nothing like a circle. It's of the same geometric family as a circle. It's a conic section for those that know what I'm talking about. But it's not a circle. Anyway, the answer was 2.16. We put more rectangles, so we got 2.415. And that's actually really nice observation there. You see, our estimate went higher. You see that? It's higher. So, and that makes sense because our estimate originally was an underestimate. It turns out, though, if you're curious, the exact area is right here. It's 8 over 3. 8 over 3 is 2 and 2/3. So I'll put a bar on the 6. So the exact area is this. And what I want to show you now is how you get the exact area. So I'm going to reveal to you how the antiderivative is related to the areas. And what we're going to do is we're going to find the exact areas. The answers were 6 and they were 8 over 3. We're going to do them in the next two examples. So these two examples are awesome because you're going to see how to get the answer exactly now. And here's the first question. Find, and let's emphasize here, find the exact area of that. So the way that you find the exact area is related to the antiderivative. And it goes as follows. First, you find the antiderivative. So this is a review of last time, and it's a review of the first week. So what I said to you from day one this semester was, we're going to show you skills for antiderivatives, and I'm going to be very repetitive. I'm going to show you them again and again and again. So there you go. We're going to find the antiderivative. Can someone tell me the antiderivative of this? Please. What's the antiderivative of 2x? Good. And if you don't know that, you better do some like warm-ups or whatever because it's on your quiz. You know your quiz is at 10 o'clock and it's based on antiderivatives, so it's still there. And what's the antiderivative of 1? Thank you, Sean. So that's x, and then remember you put a c. Remember you put a c? You always put a c. I'm going to put the c there. It turns out that when you're doing areas, you can get a little bit lazy, and if you're doing areas, you don't have to write the c. But I'm not going to be lazy with you. So here's the next part of the process. If anybody's getting scared here, you've already finished the hard part. The hard part was those tables. Now, that's A and that's B. So what does f of B equal? In other words, what is the antiderivative when x equals 2? Can someone calculate that? I'll write it down here, but I'm relying on you to make sure I don't be silly here with my math. I'll take baby steps. 2 squared, yeah, that's right, Jai. It's 2 squared plus 2 plus c, or in other words, 6 plus c. And finally, what's f of a? It's f of 0, which is, yes, that is correct. Thank you. It's 0 squared plus 0 plus c. Now, if you're wondering, what are you doing here? Like, how is this working? Like, it's related to something called the fundamental theorem of calculus. So this here is kind of like the most fundamental, I'm using the word fundamental again. It is the most important equation in calculus. It's two sides of the same coin. A and B. So the area, the exact area, is f of B minus f of A. In this case, that's going to be 6 plus c minus c. And look at that, people. The answer is 6. Isn't that cool? That's the exact answer. So all those tables that I showed you that ate up so much time of your life and the lesson today, and you could find the exact answer, and the exact answer is like, oh, get the antiderivative and stick in two numbers. Let me know your feedback in the chat. What do you think? Do you think this is cool? This is weird? Are you shocked? And isn't it so much better than the table? Nothing wrong with the table. And keep in mind, some people when they teach this, they don't use a table. They just write down a long list of numbers and add them together. And you're just like, why are these people writing all these numbers down? Now, I'm not going to lie to you. it's kind of like when you did derivatives. When you do derivatives, first you do limits, 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 and then later I show you the shortcuts. Remember that? Remember in the fall how we did the derivatives and it was painful, but then the shortcuts was the best? Yeah, exactly, Jai. And I'm just going to mention here, going from the table to going to this is first principles, and it's a proof. I'm not proving that in this course, and rarely in mathematics courses, outside of like a pure math or a physics or maybe an engineering physics, will you see an actual? It's very rare that you'll actually see the proof of it in an undergraduate level first year calculus. Usually the proof is glossed over. So we're going to get that next question. We're going to find the exact area for this one, but this time I'm just going to type it because my handwriting is way too slow for you. So first we get the antiderivative. What's the antiderivative of this function here? Let me know in the chat. What is the antiderivative of 9 minus x squared? What is the antiderivative of 9? Thank you. And then x, and what's the other one? X to the, how does it go? What goes here? You got to add 1. Remember, Amir, you got to add 1. So that's what your quiz is on today. It's that antiderivative stuff. So be careful, be ready. And then you can get f of 3. And you can get f of 2. Let's do that here. So we have 9 times 3 minus 3 cubed over 3 plus c. And 9 times 2 minus 2 cubed over 3 plus c. Well, it's just a little slow today. Yeah, I got your emails. I replied to them. I replied to them, Dante. Give me a private chat message, okay, before the quiz. Sounds good? Dante, are you there? Okay, don't worry. We'll talk just private chat. No problem. Just at the end of this lesson, there's a little bit of a break before the quiz, and we can talk briefly. No big deal. Don't worry about it. Okay, so this is 27 minus 9 plus c, which is 18 plus c. And over here we have 18, whoops, 18 minus 8 over 3 plus c. So then the exact area is the antiderivative at 3 minus the antiderivative at 2, which is equal to this minus this. Notice that the c's cancel. The c's will always cancel, or whatever constant that you use. And the answer is 8 over 3, as I mentioned earlier. So there it is, people. 8 over 3. So that was the answer that I reported here. If you can see it here in the side tab, that's the answer that I reported to you earlier and said, oh, that's the exact area. So now you see it here. So I'll just write it as a decimal. Obviously, it's a repeating decimal. But yeah, that's it. So now that you have that, really the entire story is starting to tie together. And I hope that you definitely get more comfortable with what's happening here. Because the story I've been presenting is now going to all really reach a climax by the end of today's lesson. And then we'll move on next week to just solidifying that whole process. So here's a question that's not something that we did with tables. So This one here, we're trying to find the area under the square root function from x equals 1 to x equals 4. So we didn't do a table for this one, but most certainly on your own, you could make a table and you could estimate the area. That's not a hint. I'm not trying to trick you or something. But if you have time and you want to practice that, you're more than welcome to do that. In this case, we have the square root function, which you know the graph looks like that. And we're trying to find the area from 1 to 4. So that area is definitely not a polygon. So you can't just look at it and say, oh, it's a trapezoid or something. So unfortunately, you don't want to use tables here. We're going to use our antiderivative knowledge. So we're going to get that antiderivative first by rewriting the function as an exponent like that, x to the half. And then we'll have the antiderivative, which is x to the 3 halves plus c, and then you have the thing in the front, which I called the checkerboard last time. You're dividing by 3 halves. So if you're a little bit fuzzy about what happened there, I'm doing the formula where you add 1 and divide by the same thing. So like over here was x to the 3 over 3. I'm doing that over here as well. Perhaps I can write it here. So I'm doing x to the 3 halves over 3 halves. If that's not comfortable for you, you're going to be not liking me today, because I'm for sure that you need to find the antiderivative of at least one radical or root function on your quiz today. So be forewarned. If you don't know how to do this question, don't jump right into the quiz. Go and do a couple practice or look back in your notes on it. We did practice it over the last 2 weeks, but still, anyway. So now we're going to actually we're going to evaluate the function at 4, the antiderivative, I should say, at 4 and at 1. So if you plug in 4 here, you get 2/3 of 4 to the 3 halves plus c. And then you put in 1. So I'll put a 1 there. So if you do the first one here, you can use a calculator for here, but you can do this in your head as well. I think that's 16 over 3. Can someone confirm 16 over 3 for that? Thank you. And that one's easy. Thank you. This one's a joke, because 1 to the power of anything is just 1. So this just becomes 2/3. And then we can say that the area is equal to f of 4, antiderivative at 4 minus antiderivative at 1, which is, plug in these things here. Notice that the c's cancel. So if you are a little bit lazy here, I don't want to use the lazy word in a bad way, but if you want to use the word lazy, that's fine. You can get rid of the c's. In fact, you can ignore the c here because it's going to cancel. So a lot of people will ignore the c. It's not the best thing to do, but you can do it. So that area is 14 over 3. So this area that I'm going to shade here in blue is 14 over 3. So 14 over 3. So now it's time for Coloring with John, sponsored to you by George Brown College. Yeah, you can make a decimal, but it's an exact area, Jai. So exact means fraction here, because you're never going to write enough decimals unless you put a bar. Unless you put a bar on the 3 on the decimal part. So this would be like 4.6 bar, or 6 repeating. Yeah, exactly. Even if you wrote all those 6's down, it's still not exact, because you'd have to write an infinite number of 6's to achieve the desired accuracy. Okay, my friends. Yeah, you got to put the bar like this. See over here? Look at my mouse. See that? Like that. Yeah, exactly. So to Jai's comment, you got to put the bar over the 6 if you want to put a decimal here, because this one goes forever. So it's time for that time. You know what time it is? Who knows what time it is? I'll give you a clue. Not quiz time. What G and C stand for? Let me know in that chat. Oh yeah, sort of, it seems. Guess and check. Okay, or substitution rule. I don't teach you the substitution rule in this course for reasons I mentioned earlier in the semester, but you can use guess and check or substitution rule. For this question though, I'm not going to actually do the guessing and checking. I promise you that I'll do a lot of guess and checking next time, like in the last week. But for today, I'm just going to tell you the antiderivative, because the emphasis today is not on finding the antiderivative, it's on areas. But I promise you next week, we will get questions like this, and I will walk you through them very patiently, and we'll do a bunch. But for today, I'm just giving you the antiderivative, and the reason I'm not going to walk you through it is because you have a quiz on it today, and you should know how to do it. So if you don't know how to get this answer, then you are ill prepared for the quiz today, even though you were forewarned by me several times. So that's the antiderivative. And we're going to find plug in the value 6 and the value of 0. If you put 6 in here, it's going to be ugly. So I'm going to make this ugly looking number here the best I can. That's 2/3, 37 to the 3/2. No one said math was pretty all the time. I think math's always pretty. But this question definitely does not really fancy, sorry, I don't really fancy the numbers in this question too much. But anyway, there's f of 6 and f of 0, the antiderivative at the two endpoints. So then the area, is equal to f of 6 minus f of 0. Oh no, it's not 1. What? Oh, sorry. Where do you mean 1? Tell me where you mean there's a 1. Oh shoot, yeah. Thank you. Sorry about that. Yeah, that seemed a little bit off because I was still there and I really didn't really think about that too well. My apologies, people. I'm gonna nickname Sean and Jai. If you don't like wrestling, I don't know if you ever watched wrestling as a kid. I did. I'm gonna if Sean and Jai were a tag team, I'm gonna no. Your tag team name, if Jai and Sean were a tag team, this is your tag team name. Ready? That's your tag team name. Quality control. So you two would like rule all of wrestling because you just come in there, and anybody who was not the standard, you just like beat them up. I don't mean literally beat them up. I mean like fake wrestling beat them up, and be the champions of the world. Anyway, no. The only math bully here is me. I'm the math bully. I like that word. That's a good name for a wrestling team. Math bully. I like that, Syed. That's me and Syed. We're gonna challenge you for the title. You watch. We're gonna have like a pay-per-view or something. Anyway, all jokes aside, we have enough information to answer this question now. So my final answer is this. That would be an answer that I think would be pretty. And I'm just gonna put I'm gonna just cross out the C's here because the C's cancel anyway. So that's the answer. And if you want an estimate or an approximate there, that's approximately 149 or 149 units squared, whatever the units are in this question. So there you have it. There you have it. This is how the area and the antiderivative are connected. So I have one more thing to talk to you about briefly. And then you can take some time to go and prepare for that in-class assignment / quiz. I want to go back to the beginning of today and remind you about this. We started off here, and I mentioned this formula to you last week. Remember this dx here? And I said to you, what the heck does the dx mean? Well, I hope that you have a better understanding of it now. I hope that you have a better understanding of it now, because dx here, what you can do is you can think of it as an interval width. You can think of it as follows. Because I mentioned to you that the antiderivative gives you the exact answer for the area, you can think of the symbol dx as the width of an infinitely thin rectangle. So as far as you're looking here now, since I told you that the antiderivative really is related to an area, you can think of this as the height times the base. Base times height, that's the area of a rectangle. There's your base, there's your height. It's not literally that, but it is that for an infinite number of rectangles. So it's not just one rectangle, it's an infinite number of rectangles. So how do we tie this together and make it into a nice, pretty little process? Because right now, this thing here is correct. All of the stuff here I've written down here is correct. And if you answered every question, that I gave you, or even in just any math course like this, that is perfect. There's no problem with that. But you know how mathematicians are. Mathematicians like to be efficient and clear and just all around beautiful with how they do things. So that's what we have here. This thing here is next week. So let me write this down, okay? This is next week. We're going to do a bunch of these next week. But I want to give you a preview of it today by just answering this one question so that you understand what we're going to do next week, and we can just jump right into it. This is an integral. Because of that squiggly thing there, we know that's an integral. The word definite here refers to the fact that there's numbers now. You see how last week there was no numbers here? Like your quiz today doesn't have numbers here. It's called an indefinite integral. That's today's quiz. But next week, you're going to have numbers. And the way that you do this, it's really, really easy. You take the quantity inside here, which is 3x, and you find the antiderivative, which in this case is, as you probably know, 3x squared over 2 plus c. And then what you do is, we're not done with that. I'll explain that in a second. It equals the following. 3 over 2, 2 squared plus c, and then minus 3 over 2, and then 0 squared plus c. Do you see how this stuff here is identical to what I was doing up here? Do you see how it's the exact same thing? I'm just taking the antiderivative and plugging in two numbers. Because that's actually what a definite integral does for you. It takes the process that you just saw in the previous question and it streamlines it. So instead of writing this sentence here, find the area, blah, 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 from there to there, all that stuff that I wrote, you replace it with this thing here. No words, no English, nothing. Just the formula. One last thing here, cosmetically, it's a notation. You put a line here and you put the 0 and the 2. And that's a shorthand. This thing here is a shorthand to plug in 2, plug in 0, and subtract the answer. See? Plug in 2, plug in 0, and subtract the two answers. So this thing here I'm showing you at the end, I'm going to go through it a very, very slow next time, but I thought I would just kind of get your foot in the door and just show you briefly an example so that you can say to yourself, oh, okay, I understand a little bit about it, and I can kind of plant that in my mind for next week. Those cancel, and the answer here, by the way, is 6, just to finish the question. So that's all I have for you today. Okay, don't worry, Adnan. I promise you'll have lots of fun doing these next class with me. But for the purpose of what I'll ask you next week, just be prepared to do the tables and to find the area. I want to say that again though. The quiz or assignment next week that you get, it may not have the table the exact same way. So you know I make the table here for you all pretty, whatever, or maybe you don't like the way I do the table, that's cool. You're not going to get the table the exact same way. So when you do get your in-class assignment / quiz next week on my lab, I do want you to just be able to fill it in according to whatever instructions are in that table, in that question. So I'm just going to warn you, it's not going to be identical to this because the textbook doesn't really follow this structure. It just does it all with algebra, which I'm not really a fan of. Anyway, that's all I have for you for today.